Assalamualaikum and welcome back. Now let's continue with example 2. We are asked to find the intersection curve between between the sphere and the plane y equals 2. Okay, so here we have a sphere of radius square root of 13 and we want to intersect this sphere with the plane y equals 2. Okay, let's say this is our plane y equals 2. Say square of 13 would be 3 point something. So let's say that's a 2. So for y equals 2, we have a vertical plane. And when this 2, so this is, let's say that's a y equals 2. And when we have a vertical plane, when we slice the vertical plane, when we slice the sphere with a vertical plane, what we have is a circle. Okay, what we have is a circle. So this is the circle. So the circle will be on the sphere and also on the plane. That's ugly. It's going to be on the y equals 2 plane, and it is also on the sphere. Alright, so what we want now is to get the vector valued function for our intersection curve. Okay, we want that. Alright, so what we want is a vector valued function. So we want what is ft, fti plus gtj plus htk. Now when you look at our intersection curve there, it is the intersection curve lies on both the plane and also the sphere. Okay, so this is y equals 2, the plane y equals 2, and the curve happens to be on both surfaces, the sphere and the plane. Now you can see that one of the components is always the same value, it doesn't change. Okay, so you can see that all the points on the intersection curve here, the y coordinate is always 2. The y coordinate is always 2. So from there we can say that the x component is always 2. Okay, it is always 2. It doesn't change, only x and z changes. Okay, so now we need to get the relationship between x and z with our parameter. Excuse me, parameter t. But we know the y component is always 2. Excuse me. Now let's look at our surface. Let's look at our sphere again. For our sphere, we have x squared plus y squared plus z squared equals 13. Now when y is 2, then the equation of the sphere will be reduced to this. Okay, or we can write this down as x squared plus y squared equals 13 excuse me, minus 4, which is a 9. Okay, then you can see that this is an equation of a circle of radius 3. And you can see from our intersection curve between the two spheres, between the sphere and the plane, we have a circle. So we know that the radius of that circle is 3. So the distance between here and there, that's a 3. That's a 3, and this is also a 3. Okay, so now we're going to relate x and z. Okay, because y is always 2. Just need to relate x and z with a parameter. Okay, since our excuse me, our intersection curve is a circle, Okay, I'm gonna draw a circle here. So now the circle is between x and z. Okay, and the circle is of radius 2. Let's sketch that. Excuse me. Oh dear. So we have a circle of radius 2. Sorry, 3. That's a 3. That's a 3. Negative 3. Negative 3. Okay, now if we draw a straight line here, okay, the distance between the radius here is always 3. Let's say here we have a point x and z. Okay, x and z. Alright, now we need to figure out the relationship between x and z there. We can draw a triangle. Okay, let's say this is an angle theta. Okay, now from the right triangle we can say that cos theta is adjacent divided by hypotenuse. So the adjacent here is x and hypotenuse is 3. So from there we can get x is 3 cos theta. And for sine theta, this is opposite divided by hypotenuse. So the opposite is z. Okay, and from there we get z is 3 sine theta. So from there we can relate x and z with the parameter theta, but we want to use t, so now we're going to change theta to t. So from there we can get parametric equation for x, which is 3 cos t, because we want to use t here, and for z is 3 sine t. Okay, and y is always 2. So from there we can get the vector valued function for the intersection curve between the two surfaces, the sphere and the plane y equals 2. So the intersection curve is equal to the vector function r, where the x component is 3 cos t and the y component is 2 and the z component is 3 sine t. Okay, right, so that is the vector valued function to represent the intersection curve. Thank you.